All right, guys, we have the review for your test for note cards 31 through 42. I want to remind you to make sure that you look at 39A, the one on linear approximation, overestimates and underestimates. I hope this detailed solution just helps you out so that you can review, go back and look at it and see the explanation. I am also posting online, remember, some extra some extra problems that you guys can work on as well, so make sure you look at that too, okay? In this first problem here, it's telling you to find the absolute extreme values. And when we're looking for the absolute extreme of values, we should know that we have to be working with the first derivative. So extrema should be first derivative. You need to know which derivative you use for what test. So extrema values, first derivative. So I'm going to find the first derivative of this function. We're going to use the ho d high minus high d ho over ho squared. And we should all know how to find this derivative already. So again, using the property of our quotient rule, this would be the derivative of that function. Now, of course, I need to clean it up a bit so that it'll be easier for me to work with. So I'm going to go ahead and distribute, FOIL things out, distribute the negative 1 right here, all over x plus 1 squared. Combine like terms, so we end up with x squared plus 2x minus 3 over x plus 1 squared. Now, this is my first derivative. Now, when we are trying to find the absolute extreme of values, we need to work with the first derivative equal to 0. We need to find where the critical numbers are occurring. Because remember, where critical numbers are, that's a horizontal tangent where there's a possible max or min. Okay? So just still trying to clean this up, factor it up. So x plus 1 over x squared, x plus 1 squared. Equal this to 0. Now I'm going to equal both again, numerator and denominator equal to 0 because critical numbers occur at the horizontal tangents, but they also occur when the first derivative is undefined. So therefore I have to set every single piece equal to 0. X minus 1, x plus 3, and the denominator x plus 1 squared. All of this, guys, is basic algebra. You should know how to solve these all for your x's. And those are all the x values that I get, -1, 1, and -3. Now, this particular problem had a restriction. It had a restriction on the domain. The domain was only from 0 to 2. So if I go back and look at the x values that I got, -1's not in the domain, and -3's not in the domain. So the only x value that I can test is the 1. Now, remember that when we are looking for absolute extrema values, we need to consider the endpoints and our critical number that falls within that range or that domain. Now, when we're trying to determine what's the max and min, we have to look at y values to determine max and minimum values. So we set up our table of values. I'm going to test or check the y value at 0, at 2, and at 1. Now, how do I get all these y values that I'm writing? All of these y values come from plugging it into the original function. Remember, the original function is going to give you the values at that point. And that's how I'm going to determine the absolute max and min. So now comparing these values, my absolute maximum would have to be at 0, and its value is 0, because this is the highest number between the 3 points that I am checking. The absolute minimum is going to occur at x equal to 1, and its value is -1. Again, why? Because it's the lowest value from the table that I've created. And that's how you find your absolute max and mins. You have to create a table of values. I need to find the highest and the lowest point. But before doing so, you need to find also those critical numbers, because remember that those are horizontal tangents, so the graph could be curving up or down at those points. Okay? Number 2, find the average rate of change. No, find where the average rate of change is the same as the instantaneous rate of change. That is asking you where is A rock equal to I rock. Now, how do I find A rock? AROC, remember, average rate of change is your slope formula. F of B minus F of A over B minus A. Now my B and my A are the closed interval that they're giving me. So I'm going to go ahead and label A as my 0 and B as my 2. Okay? So again, this is my A, this is my B. Those are the two X's that they're giving me. I need to find F of 0 and I need to find F of 2 so that I can plug it in to find the slope. So all I'm doing is calculating basic slope. Now how do I calculate F of 0? I want to know the value of 0 at the original function. So all I need to do is plug the 0 into this function. To find F of 2, plug F of 2, plug the 2 into the original function. So if we go ahead and we plug in the 2 into this function, we end up getting 9. And if I plug the 0 into this function, we end up with negative 1. So now that I have all my values, I'm ready to calculate the slope. So the slope would be 9 minus a negative 1, which changes to positive, over 2 minus 0, which is 10 over 2, which equals 5. So AROC, the average rate of change, equals 5. Now, how do we find IROC? IROC is the instantaneous rate of change. That is the derivative. At that instant, what's the rate of change? That's a derivative. So we find the first derivative of this formula, of this equation, which gives me 3x squared plus 1. So AROC equals IROC. 5 equals 3x squared plus 1. Now we can go ahead and we can solve this function for x. Now here on the fraction, remember that you can do each one separate. You can do the square root of 4 and the square root of 3. So that's what I went ahead and did, which it gives me plus or minus 2 over radical 3. Now remember that I am looking for that when the average rate of change is the same as the instantaneous rate of change, but I'm restricted to the domain between 0 and 2. So I have two values here. However, it needs to be a value that's within that domain. And the only one that's inside that domain is the positive one. Okay, prove whether Rolle's theorem applies for the following. Rolle's theorem tells us that there's at some point on this graph, there has to be a horizontal tangent. And there are three requirements that you need to check to see if Rolle's theorem applies. Number one, it must be continuous over the interval that's given. Number two, it must be differentiable over the interval that's given. And number three, f of a should equal f of b. So first thing, is this function continuous? Yes, it's continuous over the interval from negative 1 to 0. There is no problem with me plugging in any of those numbers into this function. Therefore, it's also differentiable within the open interval from negative 1 to 0. Again, no problems if I plug any of those values in here. Third step is I need to check that f of negative 1 equals to f of 0. How do I find those two values? I find this value by plugging it into the original function. So if I plug in a negative 1, I get negative 5. If I plug in a 0, I get 0. Are the two numbers equal to each other? No. So if the two numbers are not equal to each other, then Rolle's theorem does not apply. So in this particular one, Rolle's theorem does not apply because f of negative 1 does not equal f of 0. So I have to state which of the three steps it did not meet. Okay? Now in part B, is this a continuous function? Yes, it is over the interval from negative 1 to 1. If I look at the function, what would make it undefined is if this was a positive or negative 2. However, positive negative 2 is not in the interval. So then it is continuous. Would it be differentiable? Yes, it's also differentiable because the point that causes problems is that positive or negative 2. And again, it's not in the interval. So we're okay with that. Step 3, I need to check that f of a equals f of b. So f of negative 1 has to equal f of 1. So how do I find these values? Plug them back into the original function. So I'm plugging negative 1 in and I'm plugging 1 in. The two endpoints do come out equal. They both equal 1. Therefore, if the numbers are the same, It's continuous. It's differentiable. The two endpoints equal each other. Rolle's theorem does apply here. So what does that mean if Rolle's theorem applies? It means that there has to exist some value C in that interval from -1 to 1 such that f prime of x is equal to 0. In other words, there has to be a horizontal tangent somewhere on this graph within that interval. Okay, number 4. Now remember again, you need to know what derivative you're going to work with. So right here it's telling me to find the intervals where it's increasing or decreasing. I need the first derivative. So g prime of x will equal 8x to the third So the derivative here would equal 8x to the third minus 8x. Again, we need to set the derivative equal to 0 so that we can find the critical numbers. Factor out what they share in common. So my critical numbers are 0 and positive or -1. Now this one doesn't have a closed interval, so all three values need to be considered. So I'm going to do my number line, and I'm going to test the points with between the values of -1, 0, and 1. And in order to test these values, whatever value I pick, I have to plug back into the derivative. We don't plug back into the original. The original is to find values. To figure out if it's positive or negative within those intervals, I need to plug back into the derivative. So I pick a value less than -1, plug into the derivative. It gives me a negative. A value between -1 and 0, if I plug in and pick a point, -0.5, plug it into the derivative, gives me a positive value. A number between 0 and 1, let's say 0.5, plug into the derivative, gives me a negative. And then a number greater than 1, like 2, plug into the derivative, gives me positive. So I'm not just showing you the actual plugging in, but that's where these signs are coming from. I'm picking a number in between those values, but I plug into the derivative. The original would tell me the location of what's the actual value there. I want to know if it's increasing or decreasing. A derivative tells me a slope. So that's how we have to plug into there. So it's increasing where the values are positive, and it's positive from -1 to 0 and from 1 to positive infinity. Because, now why? Because the first derivative g prime of x is greater than 0. That little statement right here is very important for me to say why I'm saying it's increasing. Because I'm looking at the first derivative, and what am I looking at? That it's positive, it's greater than 0. Now it's decreasing where it's negative, which is from -infinity to -1 and from 0 to 1. Again, why am I saying that it's decreasing there? Because g prime of x is less than 0. Those little statements are your justification and are very, very important. Okay, part B asks for the coordinates of a relative extrema. So coordinate, I need an x and a y. Extrema, I should be working with the first derivative. Okay, so we need to find the coordinates, which is an x and y of the relative extrema. Extrema, I should be dealing with the first derivative. All right, so for the coordinate points, well, there I need to find the actual y values. So if I come back and I look at my number line I already drew, from here to here, it's decreasing then increasing. So what's being formed? A minimum. This area here is increasing then decreasing. So at 0, there's a relative maximum. Then it goes again, decreasing to increasing, so there's a relative minimum. So when I go back and I look at my number line, this is where I'm going back to verify where's there a min and a max by looking at the change in direction. So there's a relative maximum at 0, 1 because it wants to know the coordinate. How did I get 1? I plugged 0 back into the original function. There's a relative minimum at -1 and at 1. Both of these have relative minimums, again, because we looked at the direction in which it's changing, increasing to decreasing. Now, to find the y values, what do I do with these x's? I plug them back into the original. Okay, that's where the y's are all coming from. Now, how do I know that this is a relative max? Just like we said over here, because g prime of x is changing from increasing to decreasing. That's what's creating a max. So g prime is changing from positive to negative. The minimums are occurring because g prime of x is changing from a negative decreasing to increasing. That's what's creating a minimum value. Part C, intervals where where g of x is concave up. To determine concavity, we look at the second derivative. Same concept, form a number line, but we work with the second derivative. Concave up and concave down. So I need to find the second derivative of this function, which g double prime of x would equal 24x squared minus 8. Set it equal to 0 so that I can find possible points of inflection. Factor out what it shares in common and finish solving. So that's the algebra part that you guys should know how to do. So my possible points of inflection are at a positive and negative square root of 1/3. I need to set them up again on a number line, both values, the positive and the negative, and I need to pick test points in between each of the intervals. Where do I plug in the values that I'm testing? These values that I am testing need to get plugged back into the second derivative. So I pick a value less than negative square root of 1/3, it came out positive. Pick a value in between like 0, it comes out negative. Pick a value greater, comes out positive. So these are points of inflection because it did change concavity. Now this question was asking me, where is it concaving up and where is it concaving down? So it's concaving up where it's positive and it's concaving down in the interval where it's negative. So concave up from negative infinity to a negative square root of 1/3 and a square root of 1/3 to positive infinity. Now, why is it concaving up there? Because which derivative am I referring to? Second derivative is greater than 0. Concave up, second derivative has to be positive. Now it's concave down. It's concave down where my second derivative came out negative, which is from negative square root of 1/3 over to positive square root of 1/3. Again, because the second derivative is less than 0. Again, those little statements right there, guys, are very important. You have to make sure that you have those statements there. Those are your justifications. Okay? Now, part D, points of inflection and justify. Right, points means I must be giving an answer in the form of an x and a y. So point, inflection, I should be working with the second derivative. Well, we just did that in part C. And our points of inflection were both the positive and negative square root of 1/3 because it actually did change signs. So a point, I need an x and a y. I know the x's, how do you find the y values? You need to go back and plug into the original function. So when you do that, you end up getting a negative 1/9 as both y values. So again, I'm not going in and focusing so much about telling you the math behind plugging it in. You guys can plug these in so that you can find the y values. Okay? Number 5, find the intervals where y is increasing and decreasing. We actually did this one in all the classes, first, third, and fourth. So I'm going to go through it a lot quicker. You had to do product rule just so that way you see the work as it's happening, and hopefully it just refreshes you on what we did. So second times the derivative of the first plus the first times the derivative of the second. Now I'm looking for increasing and decreasing intervals, so I have to be setting that derivative equal to 0. So before doing that, we just cleaned it up a bit and combined some stuff, move negative exponents down so we can turn them to positive, so that it'll make our solving a little easier. Now, I know several of you are having difficulty on seeing how do I solve this. If you have a fraction added or subtracted to another fraction, automatically try and move one over. That way you can get a fraction equal to a fraction, which makes it so much easier to solve because all you have to do is use cross multiplication. Okay, which is exactly what we did here. So we cross multiply. I left with x plus 3. Now on the other one, when I cross multiply, I need to remember when we multiply, we add exponents. So if you rewrite this, it's like me saying 4x to the 3/4 and a negative x to the 1/4. Add your exponents, which reduces to just 1, so I'm just left with negative 4x. And then from there, you can finish solving using the basic algebra skills, and you get that x equals a negative 3/5. So again, I'm going through this one pretty quickly just because we did it already in class, so hopefully you just seeing it again reminds you of what it is that we had covered, okay? Now, when I also am working on determining intervals of increasing and decreasing, my critical numbers, of course, is where the derivative is equal to 0, but I also need to consider where the derivative is undefined. And so the derivative here would be undefined when x equals 0. So I go back and I had to check that on the denominator. So we went ahead and made a number line and we checked values. The problem here was that negative numbers do not work in this function. And the reason they don't work in this function is because I have a fourth root. And a fourth root, you cannot have a negative number inside of there. So the only numbers I could test is anything greater than 0. So I plug in a 1 and I get that it's positive when I plug back into the derivative. So it's increasing from 0 to positive infinity because the first derivative was greater than 0 there. And decreasing nowhere. Okay, because in the other ones we got does not exist. We can't plug in the values there. It's undefined. It's actually undefined in the original function itself. So again, I did go through that one pretty quickly just because we had already done it in class. All right. Now on number 6, for y prime, and it gives you y prime, find the x values of any local max and min values. Again, max and mins, I need to be working with the first derivative. They already gave me the first derivative, so I didn't have to do anything else here and find it. It's given. So I need to set my first derivative equal to 0 so I can produce the critical numbers. This one's already factored out for you too, so all you had to do was set each individual piece equal to 0 and solve. So I have 3 different critical numbers. I have x equals 1, x equals 2, and x equals 4. So I need to set them up in a number line so that we can determine local max and min. So I'm going through it pretty quick, I know, sorry guys, but how do I test values? Pick something less than 1, so I could pick 0. Well, 0 won't tell me if it's, oh no, yeah. So if I pick a 0 in here, negative 1 squared, this will give me negative 2, this will give me negative 4, so this term right here is always going to be positive. So this would be a negative times a negative, it's positive. A number greater than 1, like 1.5. Again, this is always going to be positive, negative, negative, positive. A number greater than 2, like 3. If I plug in a 3, 3 minus 2 is positive, 3 minus 4 is negative, negative times a positive, negative. A number greater than 4, like 5, 5 minus 2 is positive, 5 minus 4 is positive. Positive times positive times positive, positive. So we need to go back and you need to plug back into the first derivative so that you can get these values. Now I'm looking for local max and min, so I have to look at where the change in direction is occurring. And the change in direction is occurring at 2. At 2, it's going from increasing, then it switches to decreasing. So going from increasing to decreasing, what's being formed here? An maximum, a local max. Now, same thing on the other side. Going from decreasing, then it changes to increasing. So what's being formed in there at the 4? It's a local minimum. Now, this problem just asked you to find the x value at where there was a local min or max. So you didn't have to go back and plug in because we didn't have the original function anyways. So local max is at x equals 2 and local min is at x equals 4. Now for some of you guys, we did go over this problem in class. Or for I think 2 classes, I'm not sure, I don't remember. So I want to remind you on reading the table. When I read the table here, these values f of x are the values on the original graph, okay? So it's telling me this is an actual point, this is an actual point, this is an actual point. Then it's just telling me all the values are positive between 0 and 1, all the values are negative between 1 and 2, and all the values are negative between 2 and 3. They are restricting me to this closed interval of 0 and 3. Now, first derivative, it's undefined, it's negative between these values, it's negative between those values, it's undefined, and it's positive. Second derivative, it's undefined at 0, positive here, negative, undefined, negative. And then here it also, sorry, it equals 0 on that derivative. So let's translate what all of this means. If I'm referring to the first derivative here, let me pause that. If I'm referring to the first derivative tells me increasing or decreasing. So if this is negative, it's decreasing in this interval. It's decreasing in this interval, and it's increasing in this interval because it's positive. It's 0 here, meaning it's a horizontal tangent. It's undefined here because it's an endpoint. I can't take the derivative at the end. But it's undefined also here at 2, and 2 is a number within the interval. So what can create something to be undefined on the derivative, but it has a value? That means more than likely there's a cusp that is happening here. It's defined there, but its derivative is not. Okay? Now if I look at the second derivative tells me concavity. So the graph, it's telling me it's concaving up here because it's positive, then it's concaving down, then it's concaving down. So looking at part A, it says find the x-coordinate of each point of which f attains a local maximum value or a local minimum value. When we're looking for local max and mins, we set up our number line, and we need to check all our points. So my points are from 0 to 3. The important points that were given to me here were 0, 1, 2, and of course I need to include 3 because that's the interval that this is from. If I'm looking for a local max or min, we need to work with the first derivative. So if I come back to the chart, the first derivative between 0 and 1 is negative. Between 1 and 2 is negative. Between 2 and 3, it's positive. So let's talk now direction. The only place where they're changing direction, the only place where it's changing direction is here at 2. It's going from decreasing to increasing. So since that's where there's a change, when I go from decreasing to increasing, what can I form? A minimum. So local max, there's none. There's no change from a positive to a negative. The change is just happening from negative to positive. So the local maximum, there's none, but the local minimum is at x equals 2. And remember, this is saying local, okay? Now, the second part of this problem says, also state the x-coordinate of each point at which f contains an absolute max or min. So the difference between the local and absolute is absolute, I have to include the endpoints. So if I look at my endpoints were 0 and 3, and my critical number is 2. I'm not putting 1 in here because there's not a change in sign. We already established that there's no max or min happening at 1. Okay? There's no change in sign there. All right, so I'm going to go back to my table to figure out these values. At 0, the value is 1. At 3, I don't know. At 2, the value is negative 1. So at this point here, this graph, it's going towards 3, and I'm going to give you right now a visual so that you can see what this graph possibly looks like. But at this time right now, it's open. We don't have a value for 3. It's not included, okay? So based on the values that I have here, the absolute max is at 0, and its value is 1. The absolute min is at 2, and its value is negative 1. Now, this problem only asks for the x-coordinates. That's why I only wrote axis. All right? Okay, last part, find the x-coordinate of each point of inflection. When we talk about point of inflection, we need to always look at the second derivative. And a point of inflection only occurs if there's a change in direction. So looking up here at the second derivative, where do I see a change in direction? It changes in direction. Let me go back to that. No. Hold on, guys, because I remember I had to do this in pieces. So I recorded, and then that's why I'm going super fast explaining. Okay, so sort of replaying it. Sorry, backtracked it. Just want to go back to what I was talking about here about a point of inflection. point of inflection, you're looking at the second derivative. It only wants the x-coordinate. There has to be a change in sign in order for me to find a point of inflection. Otherwise, it's not a point of inflection. So when I go back and I look at this table here, when I focus and look at the second derivative, the only place that it actually changes from positive to negative or negative to positive is here at 1. At 2, you can see it goes negative, negative. It didn't change. So it's not a point of inflection. It has to change sign. Okay? So my point of inflection would be at 1, or at x equals 1. Now, why? Because that's where the second derivative, f double prime of x, changes from positive to negative. Okay? Now, let me give you a quick little visual of what this possible graph could look like. I'm given these points. These points were the 3 points that were given to me in the table. Then if I look at the concavity, it says it's concaving up. Let me fix that. Concaving up from 0 to 1. Then it changes to concaving down, and then it goes to concaving up. Now, at this point also, it does tell me that it's decreasing, and it's decreasing the entire way here, and then it changes to increasing. And at 2, remember that it was undefined because the derivative was undefined, was because there's probably a cusp there. So it's doing something like this: concave up, concave down, stay concave down, decrease, decrease, increase. Derivative does not define here. Again, because there's a cusp. So this is a little image of what you possibly could be seeing. So where did the absolute max occur? Right here. Where did the absolute min occur? Down here. All right. Now remember that I am going to post some other problems in that for you to be able to go back into practice for your test. So go ahead, and I'm going to post the answer key for that. I'm not going to work them out verbally through a video, but I am going to go ahead and post the answer key so that you guys can look at them and practice some more problems, okay? So test on Monday. Good luck. Make sure you study. I don't want you to be the statistics that on Monday your score comes out lower than what it should have, all right? So good luck, and tutorials on Monday morning as well.